Okay, so today what we're going to be looking at is trigonometric identities. Okay, so we're going to explain what a trigonometric identity is. Technically, a trigonometric identity is any mathematical statement that's true for all values of a given variable. Okay, so this will always be true. The left side, we know that for any kind of equation, the left side will always equal the right side. Hence, what an identity really is, it's just an equation that is held true for every scenario. Okay, sorry about the typo, guys. One of the major trigonometric identities we're going to be looking at, one that you've already been exposed to, is this quotient identity. We stated that tan theta is equal to sine theta over cosine theta. Okay, and we showed you this numerous number of times using standard form. We also show you this through the unit circle. The other type of identities that we're going to mainly be using throughout the scope of this unit, as well as this course, as well as future courses, something called the Pythagorean identities. Now, the Pythagorean identities can actually be determined by using the Pythagorean theorem, which you all know as a squared plus b squared is equal to c squared. Right, so this is the Pythagorean theorem, and we know that this is a theorem for right-angled triangles, right? So basically what this is stating here is that the sum of the squares of one side of a right angle triangle, well, two sides of a right angle triangle. So if you assume that, this is A and this is B, and you created a square here, right? If you found the area of those squares, so the sum of the areas of the squares that make up the two sides will give you the area of the square that makes up the third side, right? You can actually find, because we know that the area of a square is side length times side length, which is in this case A times A. In this case, it's B times B, right? You can basically find the side length for C by finding the square root of this area. Okay, so I think we've all been exposed to that. But we can actually apply this into standard position. So we talked about an angle in standard position. You know what, I'm going to use a different color here. We talked about an angle in standard position. So this is an angle on a Cartesian plane. An angle in standard position is where the initial arm is located on the positive x-axis. Okay, so this is your initial arm. And the terminal arm is located either on the positive x-axis or somewhere away from that, right? Let's say that this is the terminal arm, okay? And essentially, we also looked at the point where these two arms or these two rays meet as the origin, right? So the origin is basically 0 and 0. And we also looked at angles as a degree of rotation from the initial arm to the terminal arm. So the angle here would be theta. It would be located right there, right? And because if you do a full 360 rotation, eventually what you're going to get here is a circle, okay? And you guys can imagine that, right? You can't really draw a perfect circle here, but you can imagine that this would be a circle with the center of the origin, right? It would have this equation x squared plus y squared is equal to r squared, which is the equation of a circle. That's not too relevant for our scenario. What you need to understand here is the length of the terminal arm is the radius, okay? And because the terminal arm is located within a circle and it's also placed on or positioned on a Cartesian plane, we can represent the position of the terminal arm by looking at the endpoint of its arrow, right? So the tip point of this arrow. So we can write this point as x and y. Well, that point correlates with the Cartesian plane. This is the x value, that's the y value. So you can write this point as x and y. Okay, and we've showed this. And according to Pythagorean theorem, right? If we think about this this way, the Pythagorean theorem states that x squared plus y squared is equal to r squared because a squared plus b squared is equal to c squared. Right? It's not a mere coincidence that this the Pythagorean theorem is also the equation of the circle, right? It's one of the things about having a circle with a center of 0 and 0. So you can actually apply a lot of different theorems to it. So we know this is true because of the Pythagorean theorem. Okay, and if we assume that this is a unit circle, if assumed it's a unit circle, we can also think about the points x and y as cosine theta and sine theta. How do we assume that? Well, we know that sine theta is it's the opposite side, y, over the hypotenuse, which is r, which is y over 1, right? So unit circle is where the radius is 1 unit. And we talked about this previously, right? So just go back, review some of your notes, right? So according to the unit circle, sine theta is equivalent to y, right? And if we take a look at the cosine ratio, cos theta is x over r, which is x over 1, which is equivalent to x. So as a result, we can write the ratio as point xy, or point cosine theta, cosine of the angle, and sine of the angle. Okay, so we can also write it this way. And if we take this notion and we apply this into Pythagorean theorem, you can notice that x squared here in this scenario here, if you take a look at that in terms of the equation, x squared here is really cos squared theta, right? Because it's cosine theta squared, right? Y squared is sine squared theta. R squared is basically 1 squared, right? This actually creates an identity. Cos squared theta plus sine squared theta will always be equal to 1. If you add cosine of an angle squared plus sine of an angle squared, it'll always give you 1. This is one of the most primary identities, one of the most primary Pythagorean identities. One way that we can show that it works, we assume that this is the left side, cosine theta plus sine squared theta, cos squared theta plus sine squared theta, and this is the right side, which is 1. Right, if I let theta equal, let's do 30 degrees. Okay, if theta was equal to 30 degrees, if I'm just working on the left side, you're plugging in 30 for theta. So pretend that the square is on the outside, guys. Just to kind of clarify, if you have cos theta squared or sine theta squared or tan theta squared, we write it like this, right? Or if you have cos theta cubed, we write it like this. We put the power in between the theta value and the ratio. It's just conventional, so just kind of remember that, guys. So in this case, the left side, we have cosine 30 squared plus sine 30 squared. And if we calculate this, cosine 30 squared is square root, and this is something that you need to know because these are special angles. Square root 3 over 2 squared plus sine 30 squared is 1/2 squared, which is basically square root 3 over 2 squared is 3 over 4, plus 1/2 squared is 1 over 4, which is 4 over 4. You can actually notice that's equal to 1. And what we'd say here is, therefore, the left side is equal to the right side. Doesn't matter what angle you plug into this equation, it will always be true. And that's what an identity is. Okay, so this is one of our most primary identities, guys. From this, we can actually create the other identities that you're going to be using. Okay. So one way we can show that, let me make some space here, actually. But hopefully you guys understand the Pythagorean theorem by now. It is one of the most fundamental math topics you would have talked about in your previous math courses. Okay, so using this notion, x squared plus y squared is equal to r squared, we have cos squared theta plus sine squared theta is equal to 1. And using these ideas here, and also using the quotient identity, let's say we have x squared plus y squared is equal to r squared, and I divide all my terms by x squared. Okay, so x squared divided by x squared is 1. Y squared divided by x squared is y over x squared. And r squared divided by x squared is r over x squared. Now, a few things here, right? If we think about what our ratios are going to be, right? We have sine, we have cosine. We can also write down tan here, right? If we write tan theta, in terms of this, it's basically y over x, which is a good indicator that, this is sine theta over cosine theta, right? Which is what we have. But you can also take a look at the reciprocal ratios, right? So the reciprocal ratios in this scenario can basically be cosecant theta, which should be the reverse of sine theta, right? So it should be 1 over y. Secant theta is basically 1 over x, right? And in this case, because we're using the unit circle, guys, Think about it as r over y, r over x, which is equivalent to 1 over y, 1 over x. Right, and then cotangent theta would be basically x over y. Okay, so keep these reciprocal ratios in mind, and let's apply this notion here. We divided all of our terms by x squared, right? In this case, you have y over x. Well, y over x is associated with tan theta, right? Because we had y over x here, right? So this is 1 plus tan squared theta, because we have tan theta squared, is equal to r over x, which is basically secant squared theta. This is another Pythagorean identity that we can always prove. And you guys can test that. You can plug in angle values, and you'll find that the left side will always equal the right side. And another formula that we can actually derive from this, if you have x squared plus y squared is equal to r squared, let's say we divide every term by y squared. And the reason we can do this is because if you do the same modification to one term and you repeat it to all the terms, you haven't changed the equation, right? So it's kind of the golden rule in terms of equations, algebra, and so forth, that if you have the same change for all terms within the equation or the expression, you haven't really changed anything, right? So you've kept it the same. So in that sense, you are able to do that, right? It's only when you add or you subtract from one side of the equation or expression, and you don't offset it by doing the opposite operation, then that's when you'll change the expression or equation. Okay. So in this scenario, you have x over y squared plus y squared divided by y squared is 1 is equal to r over y squared. Okay, so this is basically what your expression will look like. X over y we said was, I think it's mentioned here, it's cotangent squared theta plus 1 is equal to r over y, which is basically, I think we wrote it somewhere here, r over y is cosecant squared theta. So yet again, we have another Pythagorean identity. And there's 3 Pythagorean identities that you need to know, guys. So that's really the idea. And one way is you don't need to prove it every time. I'm just showing you how the proof gets created. That's why they're called Pythagorean identities, because we've derived them from Pythagorean theorem. But at the end of the day, I need you to have this memorized. Okay, so write it down, do questions, and you can always use them in scenarios. Okay, 1 second. So let's take a look at an example. We want to prove the Pythagorean identity for sine squared theta plus cos squared theta is equal to 1 for all angles where theta is between 0 degrees and 360 degrees. So I already kind of did this. I did this with 30 degrees. Let's just test another value. You can use any angle. I'm ideally using special angles because we know the exact values of them, right? So that way you don't have to worry about plugging into your calculator. So let's test another special angle. Let's do 60 degrees, right? You have your left side, you have your right side, right? Sine squared theta plus cos squared theta is equal to 1, right? And let's say I plug in theta is equal to 60 degrees. So you have sine 60 squared plus cosine 60 squared is equal to 1. Sine 60 squared is basically, well, we know that sine 60 is square root 3 over 2. This whole thing is squared. Cosine 60 squared, cosine 60 is 1/2 squared. Square root 3 over 2 squared is basically 3 over 4, right? Because you're doing square root 3 over 2 times square root 3 over 2. Or you can apply the square to both ends. I'm sure you know how to work with radicals, guys. The two square roots would cancel out. You get 3, and then 2 times 2 is 4. Okay, so you get 3 over 4 plus 1/2 squared is 1 over 4, and you basically end up with 4 over 4. Okay, so hopefully you can see that, right? And you can notice that 4 over 4 is equivalent to 1. So this implies that therefore the left side is equal to the right side. And when we're proving identities, we're going to be making this statement, therefore left side is equal to right side. And I'll show you some tricks or some strategies that you can use to approach identities. Not all the questions are going to be the same style questions, right? So you're going to have to get used to approaching a variety of different questions, right? But we'll look at some common strategies that we can do to take a look at these cases, okay? So what I would recommend you guys to do is test out another value. You could do another special angle. You could do pi over. Oh, sorry, I was gonna write this in radians, right? You guys can do 45 degrees. You can do 90 degrees, 180 degrees, 270 degrees, and 360 degrees. You can test any of these values, but you'll always find that the left side will equal the right side. Okay, so that's one of the tenets of an identity. Let's take a look at another sample problem. So here we want to prove that 1 plus cotangent squared theta is equal to cosecant theta squared theta for all angles theta between 0 and 360, except 0, 180, and 360. Okay, well, let's first prove it, and then let's show why these are exceptions. Okay, you guys can notice that this is one of the actual equations that we derived in the Cartesian plane using the Pythagorean theorem. Right, this was one of our Pythagorean identities. Right. But if we wanted to prove it, well, we know a few things, right? We know that tan theta is always going to be equal. Sorry, guys, let me just clean that up. We know that tan theta will always be equal to sine theta over cosine theta. This is actually its own identity, right? This is called the quotient identity. Okay, so this is already an identity that we already know, right? So this is a quotient identity. As a result, its reciprocal cotangent theta should be cosine theta over sine theta, right? This is basically the reciprocal identity of tan theta, right? You don't have to write it as reciprocal identity, but this is also an identity because it's always true, right? So having said this, let's take a look at this equation here. You have 1 plus cotangent squared theta is equal to cosecant squared theta, right? And in this scenario, you want to make the left side equal to the right side, right? So if you're trying to convert the left side into the right side, let's work with the left side. So you have 1 plus cotangent squared theta. Well, we can imagine we want to convert it to the right side. The whole thing about proving identities is that you only want to work with one side. It doesn't mean that you are exclusively working with one side. Sometimes you can simplify the other side. But in common practice, we're going to work with one side and convert it into the other side. I'm going to work with the left side. I'm going to work with the left side. I'm going to convert it to the right side because I have more terms to work with on the left side, right? So it gives me more of a chance to simplify. Okay, so let's think about simplifying the left side, right? So we know that 1 plus cotangent squared theta is basically 1 plus cos squared theta over sine squared theta. Okay, so we know this statement. And if you wanted to simplify this even further, 1 is basically, you can think about this as 1 over 1. You can convert this into sine squared theta over sine squared theta plus cos squared theta over sine squared theta. And effectively, if we group because the denominators of the fractions are the same, we can just make it a common denominator. So this is sine squared theta. For the numerator, we get sine squared theta plus cos squared theta. And because we know our primary Pythagorean identity, we know that sine squared theta plus cos squared theta is equal to 1. Therefore, this portion here will give us 1 over sine squared theta. And because 1 over sine squared theta is a reciprocal identity, it is equal to cosecant squared theta. And you guys can notice that we've converted the left side into the right side. And that's what proving an identity is. You just have to show your work because the equation is already true, right? You just have to show your work to prove all the steps. So your last statement after you've shown all your work and gotten to the other side, you just say, therefore, the left side is equal to the right side. Okay, so that's the idea behind that. So that's basically how you want to approach proving identities, right? So let's take a look at a more complicated problem. Oh, sorry, I think what I forgot to do here, so just jumping the gun a little bit. So what they're asking you to do here is they want you to also show that this is true for all angles except for 0 degrees, 180 degrees, and 360 degrees. Now, why don't those work, right? Well, if you think about what cosecant squared theta is, right? And if you think about cotangent squared theta squared theta is cos squared theta over sine squared theta, right? Now you can imagine that, whoops, let me just clean that up a little bit. You can imagine that for these values of 0, 180, and 360, the denominator sine 0 degrees squared is equal to sine 180 degrees squared, which is equal to sine 360 degrees squared, which is all equal to 0, right? All of these values of sine, the sine ratio will give you 0. And we know that if a denominator is 0, that implies there is a restriction, right? It's technically a vertical asymptote. You can imagine the same thing for cosecant squared theta, which is 1 over sine squared theta, right? These are values that will make the denominator 0. So in both cases, this is actually a restriction. So because it makes the denominator 0, we would just write this as restriction, right? Where x cannot be 0 degrees, 180 degrees, and 360 degrees. And this is for that domain indicated. And usually when we're solving these questions, we're usually going to be looking at the domain where x or theta is between 0 degrees and 360 degrees. Right, so instead of writing x, we can write theta. You can always see x instead of replacing theta for most cases. It's just our more primary variable, but these are values will make the denominator 0. So that's one of the reasons why, yeah, the identity works for all scenarios except for these values because they don't exist. Okay, and one way I could show you that it works for all variables, let's say, theta was equal to 45 degrees. We have 1 plus cotangent squared theta. Maybe I'll use a different color here so I can see this better. Okay, so you have 1 plus cotangent squared theta is equal to cosecant squared theta. Theta is 45 degrees, so you have 1 plus cotangent 45 degrees squared is equal to cosecant 45 degrees squared. And if I look at just the left side here, well, 1 plus cotangent 45, we know that tan 45 is 1, so cotangent 45 is just 1 over tan 45. Either way, that's going to give you 1, right? And this is going to give you a value of 1 plus 1 squared, which is 2. Okay, this is the value of the left side. On the right side, right, cosecant 45 is basically 1 over sine 45. And sine 45 is 1 over square root 2 over 2, which is 2 over square root 2. Now, if you imagine if you have this value squared, right, if you have square root, right out of space here, let's just do it here. If you have 2 square root 2 squared, right, because we're looking at cosecant 45 squared, right, if you have this value squared, then we should have 4 over square root 2 squared is 2, which is 2. So you can actually see that the right side is also equal to 2. So this identity actually works. The only scenarios where it doesn't work is where there's restrictions that occur. So these values 0, 180, and 360. So hopefully you can appreciate that and understand that. Okay, so let's take a look at sample problem 3. We're proving identities, and we want to prove that tan theta, or in this case, they're using phi. Let's call it theta. Okay, so tan theta is equal to sine theta plus sine squared theta over cosine theta plus 1 plus sine theta, right? Just the variable. And in this case, sorry, give me 1 second. Right, so if we're trying to prove this identity, I'm just calling theta. You just call it phi, right? The same thing. This is phi. It's just another Greek letter. This is theta, right? We'll just assume that phi is theta, right? So it's the same thing. It's just easier to draw, and I think you guys are used to it. It's just the letter, guys, right? Don't get too confused regarding that. You want to prove that tan theta is equal to this, right? For all angles between 0 degrees and 360 degrees, where cosine theta cannot equal theta, 0, sorry. If we're proving that tan theta is equal to this, I'm going to work with the right side. So the right side here is sine theta plus sine squared theta over cosine theta times 1 plus sine theta. Okay, I want to work with this side. And usually the rule of thumb is work with the side with the more number of terms because it gives you more opportunities to simplify, okay? So what I'm going to do is I'm going to work with the right side. I'm going to try to get to the left side. So the left side here, right, I know I flipped the directions, but the left side was tan theta, right? I'm working with it here. And I'm working with the right side. So essentially, let's take a look at the numerator. You can notice that on the numerator, I can factor out a sine theta because it's a common factor. So you get 1 plus sine theta. On the denominator, I have cosine theta and 1 plus sine theta. Because you have a common factor, you can cancel these out. And you're left with sine theta over cosine theta, which we know a part of the quotient identity, this is just tan theta. So this tells us, and this is equal to the left side, so this tells us that the left side is equal to the right side. And this is going to be true. And if you guys wanted to test this, right, and you don't, unless the question is asking you guys, you don't need to test it, but you do need to prove it, because when the question asks you to prove an identity, you need to show the steps, and the very last step you can write, therefore left side is equal to right side, or right side is equal to left side, depending on which side you started with, right? Unless the question asks you specifically to test a value, if you are going to test a value, let's test a special angle, right? Now you have to also note you have to note restrictions, right, of the expression of the identity that you're testing. Like in this case, I wouldn't test pi over 2 or 3 pi over 2 because of the fact that tan pi over 2 and tan 3 pi over 2 doesn't exist, and also pi over 2 and 3 pi over 2 would make the right side, the denominator, 0, which would be undefined. Okay, so I wouldn't test those values. Let's test pi over 6. Okay, oh, sorry guys. So used to teaching my grade 12s that that's the radian form of measuring angles. Let's test 30 degrees, and this is pi over 2 and 3 pi over 2 is at 90 degrees and 270 degrees. Sorry about that. That's the radian measurement of angles. That's something that you'll learn in future courses. Okay, so we know that theta cannot be 90 degrees or 270 degrees because in both of those cases it'll be undefined. Right, like tan 90 and tan 270 doesn't exist. Okay, so there's a little slip up there. Let's test that theta is equal to 30 degrees. Whoops, sorry guys. How did that happen? Let's test theta is equal to 30 degrees. Okay, so if we're testing theta is equal to 30 degrees, what I'm going to do here is I'm going to plug it into my right side, right? So sine 30 degrees plus sine 30 squared, right? You have to recall that sine squared theta is the same as writing sine theta squared, and and so forth with all the other ratios. Okay, so just remember that in the back of your mind. Denominator, you have cosine 30 degrees plus 1 plus sine 30 degrees. Now, sine 30 is a special angle, so please remember the values, the exact value for that. So if we are going to implement those values, sine 30 is a half. Sine 30 squared is 1/2 squared. Cosine 30 is square root of 3 over 2. And 1 plus sine 30 is 1 plus 1/2. Okay, let's simplify this. So this is 1/2 plus 1/2 squared is 1/4 over square root 3 over 2 plus this looks like 3 over 2. Okay, and if I simplify this, you can think about this as 2 over 4, right? So this is 3 over 4. If I simplify this, this is just square root 3 plus 3 over 2. This is a common denominator. And at this point, what you can see here is this is 3 over 4 times, because you're dividing it, you are multiplying the reciprocal of the fraction, right? So in that case, you get 6 over 4 square root 3 plus 3. And if you simplify this further, let's divide this by 2. So this is 3. Let's divide this by 2. So that's a 2. You get 3 over 2 square root 3 plus 6 because I'm expanding this to both terms. Right. Now, the thing about radicals is that you don't want to have a radical. You always want to rationalize a radical if there is a radical in the denominator. So one way, and this is something that we previously talked about, but one way you can rationalize a radical is you can multiply by its conjugate, as shown, right? If you multiply by its conjugate, you get 3 times 2 square root 3 minus 6 over 4 times 3 minus 36. Okay, so I'm just using the a plus b, a minus b template for multiplying, right? It's going to give you a product that's a difference of squares. And if you simplify this further, this is 3 So this is 6 square root 3. Let's simplify the denominator first. 12 minus 36 is negative 24. Right? If you divide this by 3 and this by 3, this is 1, this is negative 8. Right? So this is basically negative 2 square root 3 minus 6 over negative 8. Okay, now that doesn't look, for some reason, I think that doesn't look right. Tan 30 should give you square root 3 over 3. That's weird. I could have made a mistake. 1/2, 1/4, that's 3 over 4, okay. Square root 3 over 2, and then this is 1/2, so this is 3 over 2. Okay. And this was square root 3 plus 3 over 2, and then we multiplied this. Why is the answer off? 4. Trying to see here. Well, mistakes do happen. So let's do, I think this was 3, 2 square root 3 minus 6. Looks good so far. Negative 8, and then we'll just continue expanding this out maybe. We'll see if the answer gives us the same value. So this is basically this over negative 8 plus 6 over 8. And collectively, it should give us square root 3 over 4 plus 3 over 4. So this is square root 3 plus 3 over 4. Now, it's not exactly the same as square root 3 over 3. Let me see if that... That's interesting. Should have worked, actually. Okay. Okay, so to summarize, we looked at identities, which we stated was basically an equation or expression that is true for all scenarios, right? And we looked at some different types of identities. The reciprocal identities you've already been exposed to. We looked at the quotient identities, right? The reciprocal identities are just like cosecant theta, which is a reciprocal of sine theta, secant theta, which is reciprocal of cosine theta, cotangent theta, which is the reciprocal of tan theta. Quotient identities are really important because we showed using the unit circle as well as an angle in standard position on the Cartesian plane that tan theta is sine theta over cosine theta, right? As a result, it's reciprocal cotangent theta should be the opposite, okay? And what we talked about today was these Pythagorean identities, which we derived using the Pythagorean theorem. And what you need to understand when you're proving these identities, and these are just some tips that you guys can use, right? So just some strategies, right? These are just some strategies that you want to kind of use when you're proving. But at the very end of the day, try to look at the side with the more number of terms and try to just work with that single side to convert it into the other side, right? Write down all of your identities. If you don't have it memorized, write it down on a separate piece of paper, take a look at which ones apply and show all your work. And at the very end of the work, after you've shown that one side can be converted to the other side, then you can make the statement, therefore left side is equal to right side, or vice versa. Okay, so at the end of the day, guys, it does require a lot of practice. And one other thing is factoring. You need to be able to factor, right? So factoring is very key because this is very algebraic, right? So you need to kind of review some of your factoring techniques and so forth, okay? And so what I would really tell you to do, know all of these identities, but also, try to think about how to factor a squared minus b squared, right? This is the difference of squares, which you would have factored as a plus b, a minus b. Know how to factor quadratics, of course, right? Ax squared plus bx plus c, right? And you can think about how you can factor that, right? So know these factoring techniques and just in general, some of these identities. And at the end of the day, you got to do practice, right? So practice is what's going to really help you with this. There isn't just going to be one question that's like one size fits all. You have to know some of these strategies to approach a multitude of questions. Okay. So speaking of questions, here are a series of identities. Right. So what I'm going to do is I'm going to do a few samples to get you guys familiar with the idea. Right. But at the end of the day, these questions are going to be a very huge portion of the test. So get used to working through these. Okay. So let's take a look at. Let me take a look at 5b here. Okay, so tan theta over cosine theta is equal to sine theta over 1 minus sine squared theta. So have your identities in front of you. Try approaching these questions. If you're taking a look at this question, now you have to pick a side. Which side are you going to pick, right? And in this scenario, it seems like, there's 2 terms on the left side. There's 3 terms on the right side. It's really your call on what side you want to pick. Let's say I pick the right side. It doesn't matter what side you pick, right? But usually what we do is we try to aim for the side with more number of terms because it gives us more opportunities to simplify. Taking a look at the right side, you have sine theta over 1 minus sine squared theta. Whenever you see a square theta and you see sine squared theta, and you see a 1, you got to think about this identity. Sine squared theta plus cos squared theta is equal to 1. And if you actually move the sine squared theta to the other side, you can notice that cos squared theta is 1 minus sine squared theta. Right? So this is from really the first Pythagorean identity and one of the most fundamental Pythagorean identities that we looked at. And technically, 1 minus sine squared theta can be written as cos squared theta. So this is basically sine theta over cos squared theta is what this statement can be written as. Now, if you think about this, sine theta over cos squared theta is sine theta over cos theta times 1 over cosine theta. We know that sine theta over cosine theta is tan theta. Now, the reason I followed this progression of simplifying is because on the left side, which I'm trying to convert my right side into, on the left side you can notice there's a tan. And you know that if you want to convert sine theta and cosine theta into tan, you have to look at the quotient identity. Tan theta is equal to sine theta over cosine theta. Okay, so some of these identities are just, it's a mental exercise, but you would need to know factoring and your identities really well, right? So have that in front of you. Just do questions, guys, is the best way to learn this. So now you have tan theta times 1 over cosine theta. And because the left side looks like tan theta over cosine theta, you can immediately see that now because the cosine theta would be on the denominator. So at this stage, you've effectively proven that the right side is equal to the left side, so you can make the statement the right side is equal to the left side. If you started with the left side first and you're converting it into the right side, you would say, therefore, the left side is equal to the right side. Okay, so try to understand that it doesn't matter which way you approach it, right? Like let's say I worked with the left side instead, right? You only have to do with one side. You guys don't have to do both sides. It's a little time consuming, but if you feel like you have more time and you want to just test your ability to solve these Pythagorean theorem, by all means, go for it. So if I'm looking with the left side instead of the right side, I want to convert the left side into the right side. Well, on my left side here, you have tan theta and cosine theta. On the right side, I only have sine theta and variance of sine theta, right? So, and that's a good indicator that you need to get rid of cosine theta. You need to convert tan theta in the form of sine theta. And the way you can do that, we know tan theta is sine theta over cosine theta. If I plug that into the equation, you get sine theta over cosine theta over cosine theta, which is basically, sorry guys, let me just clean that up. Sine theta over cosine theta. If you're dividing by cosine theta, you're multiplying by 1 over cosine theta, right? And if you look at this, this is basically sine theta over cos squared theta, which is essentially what we had at this point. But because on the right side, we just have sine theta, cos squared theta, if you take a look at this Pythagorean identity, is sine theta over 1 minus sine squared theta, which is basically what the right side looks like. In this case, you would say, therefore, the left side is equal to the right side. So it's very important you show your work, guys. If you don't show your work, all your answers your answer is basically your work. If you don't show the steps properly, you won't get marks for this. Okay. On the outside of it, you can also put relevant formulas and stuff just to show me that you understand it. But that's really the idea, right? It's all communication, really. Okay, so try to understand that. Okay, so let's take a look at another sample here, just to kind of get you guys used to this. I'm just gonna make some space. Okay, let's take a look at 5D as well. So 1 minus cos squared theta is equal to sine theta, cosine theta, tan theta, right? So you can choose which side you want to work with. I'm going to work with the side with more number of terms because it gives me more opportunities to simplify. I'm going to work with the right side, right? So you have sine theta times cosine theta. Tan theta you can write as sine theta over cosine theta, right? And if you multiply this, you can see that cosine theta divided by cosine theta is 1. Sine theta times sine theta is sine squared theta. And we know that from the Pythagorean identity, sine squared theta plus cos squared theta is equal to 1. Sine squared theta is equal to 1 minus cos squared theta. So this, in fact, is 1 minus cos squared theta, which is essentially the left side. So all we have to do here is write, therefore the right side is equal to the left side. So write whatever side you're working with first, and then it's equal to the other side. Okay, that's the idea. That's all you have to do, guys. Another question that I also want to take a look at, let's take a look at question 7, where you're just simplifying a trig expression. So that because there's not an equation here, you would just assume that you're just making, whenever we hear the word simplify, guys, it means you're contracting the expression, right? You're making it smaller, but it's equivalent. So in 7D, we have cosecant squared theta minus 3 cosecant theta plus 2 over cosecant squared theta minus 1. Now this one is a little challenging because you can notice that it has a square term, a term with the power of 1, and a constant, right? You can actually view this as a quadratic if you do a substitution, right? Whenever you have a square term, a term that has a degree of 1 and a constant, well, you can think about this as a format of ax squared plus bx plus c. Having said that, if I let a equal cosecant theta, and you can do the substitution because you have repeating values, right? If a is equal to cosecant theta, and you get a squared minus 3a plus 2, over on the denominator you would get a squared minus 1. And this makes it look a lot easier, right? And if you simplify this, well, if you factor this quadratic out, you would get a minus 2, a minus 1, right? This is basically because the coefficient, the leading term's coefficient is 1. So you can just factor it out very quickly. A squared minus 1 is difference of squares, which is a plus 1, a minus 1. And you can notice here that the a minus 1 factors or common factors, they cancel out. So you're left with a minus 2 over a plus 1. Now if you resubstitute a was equal to cosecant theta back into this expression, you can notice that you'll get cosecant theta minus 2 over cosecant theta plus 1. And that is your simplified expression. So try to understand that, guys. Okay. And you're going to see questions like this, and not just identities, but you're going to see questions where they're going to ask you to simplify the expression and so forth. Okay, so keep that in mind. So there's a lot more questions here. I would really tell you to go through them, right? So what I'm going to do here is I'm going to get you guys to go through a few questions, specifically E, F. You could try. These are thinking questions. One of these will come up. These thinking style questions will come up on your test, on the thinking section. So please learn how to do this, right? Maybe try one of these. Some of them are really heavy, right? Try this, is also that as well. Try some of these questions, guys, and then I'll give you a few minutes, and then we'll take up some of them that you might have issues with. Okay.